Our prediction of molar heat capacity at constant volume equal to 3 by 2R, which is equal to 12.5 joule per mole per Kelvin, matches pretty well with our real gases, monatomic real gases, for example, helium, argon. However, the calculated value of CV does not match with diatomic or polyatomic gases, for example, nitrogen, oxygen, or methane, ammonia, carbon dioxide. So we need um, uh, explain the reasons for this discrepancy by considering the possibility that molecules with more than one atom can store internal energy in forms other than translational kinetic energy. So let's look at this figure. Um, um, this figure shows models of helium, a monatomic molecule containing a single atom of helium, oxygen, a diatomic molecule containing 2 atoms of oxygen, and methane, a polyatomic molecule. From such models, we would assume that all 3 types of molecules can have translational motions, say moving left to right or up and down, and rotational motions is spinning about an axis. So this is spinning about an axis like a top. In addition, we would assume that the diatomic and polyatomic molecules can have oscillatory motions, with the atoms oscillating slightly towards and away from one another, as if attached to opposite ends of a spring. To keep account of the various ways in which energy can be stored in a gas, James Clerk Maxwell introduced the theorem, what we know as equipartition of energy. So equipartition of energy states that each velocity component has an associated kinetic energy per molecule of half Boltzmann constant times temperature in Kelvin, or half RT per mole. So let's apply this theorem of equipartition of energy to the translational and rotational motions of molecules in this figure. For the translation motion, superimpose an XYZ coordinate system on any gas. The molecules will, in general, have velocity components along all 3 axes. Thus, gas molecules of all types have 3 degrees of translational freedom, 3 ways to move in translation, and on average an associated energy of 3 times half kT per molecule. For the rotational motion, imagine the origin of our XYZ coordinate system at the center of each molecule in these figures. In a gas, each molecule should be able to rotate with an angular velocity component along each of the 3 axes. So each gas should have 3 degrees of rotational freedom and on average an additional energy of 3 times half kT per molecule. However, experiment shows that this is true only for polyatomic molecules. According to quantum theory, the physics dealing with the allowed motion and energies of molecules and atoms, a monatomic gas molecule does not rotate and so has no rotational energy. A single atom cannot rotate like a top. A diatomic molecule can rotate like a top only about axis perpendicular to the line connecting the atoms. So for example, oxygen can rotate along this axis, let's say y-axis, so it can rotate on this axis, or it can rotate this. It cannot rotate along the axis joining the 2 atoms. So that way oxygen will have 5 degrees of freedom, right? So in additional 2 degrees of freedom, so it will have 5 times half kT. Methane can have 3 degrees of translational and 3 degrees of rotational motion. Also, it can have vibrational degree of freedom. So for oxygen or diatomic molecule, CV will be equal to 5/2 times R, and that is, if I use R is equal to 8.314 joule per mole per Kelvin, this number comes out to be 20.79 joule per mole per Kelvin, which matches very well with the experimentally measured values of diatomic molecule. This diagram shows dependence of CV on temperature, or this is experimental value of CV for hydrogen gas at various temperature. Because rotational and vibrational or oscillatory motion begins at certain energies, only translational or translation is possible at very low temperatures. As the temperature increases, rotational motion can begin. At still higher temperatures, oscillatory motion can begin too.